we're looking at the, I think Al-Khwarizmi publishing this compendium of Al-Jabar or Muqabala, completion and balancing, and that was a fantastic book at the time, which gave a systematic method for solution of algebraic equations. It was so fantastic that when they translated that to Latin in 1145, that is after another 300 years, everything takes 200, 300 years in evolution of mathematics. You can see that around 12th century, this book was translated to Latin, this book of Al-Khwarizmi. And the Italian translator who translated this had a couple of small problems, like I said, language problems. First was with this name only, Al-Khwarizmi. You can't write that in Latin. So he wrote that name of the author as Al-Gorithmi. And the second was this Al-Jabar. You Latinize this. Everything they Latinize. Al-Jabar was written as algebra. So a book in Latin was published around 12th century, which is a book on algebra. Original author is a Al-Gorithmi, right? And it was so fantastic. I think Khwarizmi also started a school where they started teaching children about decimal arithmetic and solving quadratic equations, all that. What we do in middle school or primary school here, he started that in that time. So obviously he is known as father of algebra. I mean, I think there is absolutely no question who the father of algebra is. Al-Khwarizmi, right? Original algebra might have come from Aryabhatta or Brahmagupta or Bhaskaracharya, one of those Hindu scholars, but then credit is given there. So we accept it. That's fine. So he's the father of algebra. Second, more important, and the reason also, there is a reason for it. See, one of the interests of these Hindu or Indian scholars, they were not interested in material things. Their interest was more on spiritual aspects of life. So they never really bothered about taking credit or getting money for a knowledge and so on. So these kind of things, definitely I don't want to charge you fees for attending this class. So, I mean, that's the kind of mentality that Indians have. Obviously, they never bothered about it. So, whereas those people probably they require that kind of credit. So it is fine. We accept that. And he was, of course, original far thinker. There is no doubt that Khwarizmi was a brilliant scholar in mathematics because he could think far ahead. And what he saw was this Aryabhatiya is a very good document. It contains a lot of gems, gems of mathematics. But then it contains a lot of pebbles also. Pebbles probably refers to our Hindu spiritual gods and goddesses who were there as part of that, I suppose. But the presentation was, like I said, strictly Sanskrit, which nobody understands. So whereas he presented it in a very systematic way, and he symbolized those variables and so on, what we call XYZ today, I think he started first time doing that in algebra. So obviously algebra, he is the father of algebra. I mean, there is no algebra started with him only. We did not have algebra. We had arithmetic and describing that in a series of words, right? Even the sinus table or the Jya table that Aryabhatta gave, that was described as a series of poem type of thing. So we never did that in a systematic way in which science should be really done. So one of the reasons I think is why he is known as a father of algebra. There is no questions on it. And one next person who comes to our attention is a gentleman, Tycho Brahe. He was actually a lord or something in one of those European countries. In fact, one last aspect of Al-Khwarizmi is that algebra name came to the subject as a new subject in mathematics. Secondly, his name itself, Latinized name itself, is used today for algorithms. What we call algorithms is a Latinized version of his name actually. Algorithm is write in programming languages. We write a series of steps to be followed. Step 1, 2, 3, 10 steps are there. Anybody follows these 10 steps, they'll get a result. So that is the meaning of algorithm. And he is the author of that original thinker who gave algorithm a meaning. So we use his name only. His name itself is used for algorithms. That is the second homage that we pay to Al-Khwarizmi. Now, next, one more very important, not mathematician, astronomer, Tycho Brahe. He was not so much interested in mathematics as such as in astronomy, and he wanted to do observations. Even though I think Galileo had invented the telescope a few years earlier, probably it was not popular at that time, so most of his documented numbers are from naked eye documentation of positions. And obviously Mars, like I mentioned before, is the most difficult planet to observe because of its retrograde motion occasionally and so on. So his business was simply sit down. He spent his lifetime, something like 20 years, in observing the position of Mars every day. So he did that and he recorded that very methodically. He set up an observatory. That's why the way he organized this whole business, where he conducted observations of Mars as a planet and recorded that as a series of ledgers or books or whatever, and that's the scientific method which was not there earlier. So Tycho Brahe is given the title is the father of scientific experimentation or observation, whatever. He is the father of something because of that great thing that he did. The only thing is, whatever numbers he got is good, fantastic, except that somebody has to make head or tail of that position of Mars. Somebody has to understand why Mars is going like that or not going like that and so on. So we needed somebody else to understand that. And around this time, we had a Polish astronomer by the name Copernicus. I have not written his name there. I suppose I could have written it somewhere there. He proposed the next theory of the universe, or this, what we call heliocentric theory. All this while, even though there had been some suggestions earlier, even among Greeks, some of them probably thought that sun was the center of our part of the universe and not the earth. Aryabhata definitely believed that earth was revolving around itself, now spinning, that he believed. We had one more mathematician, philosopher around this time, Brahmagupta. He actually believed that sun was actually attracting the planets, some kind of a gravitational attraction, and that he called it Gurutva Karshanam. So Gurutva Karshanam, I don't know how that got missed, but it was known about 600, 800 years earlier. It was proposed, not known as such, at least as a theory. None of these people were aware of that, and till Newton came around, till Isaac Newton, nobody bothered about this, right? One reason I can think of is that the Muslim mathematicians who translated, first thing, see, remember, it had to be translated always, all documents from Sanskrit to Arabic and from there to Latin, right? So one of those translators might have thought, what is Gurutva? Guru means what? As a teacher also, no? So they may not have realized it's actually a technical term for force of gravity. That's the meaning of that word in English, right? If they had known that, probably somebody else could have come up with the gravitation law earlier than Newton. That's what I'm saying. Anyway, that didn't happen. Doesn't matter. Copernicus presented this heliocentric system where sun is supposed to be at the center of the solar system with all the planets going around in circles, right? So that is what he proposed. That theory was going around in the minds of people, many people earlier, but then nobody actually put it forward as a proper scientific thesis. No, so they have to do that. So, and Copernicus did that. And Galileo, I suppose, with Galilean telescope, you could probably verify some of those informations. And in fact, he did that even before Tycho Brahe's observations. Tycho Brahe still didn't believe in the heliocentric system. He still believed in some kind of a combination of geocentric and heliocentric. It's a geocentric in the sense that Earth is center of the universe, but all other planets are going around Sun. And the Sun, along with all the planets, is going around the Earth. If you can visualize that, is something like Jupiter's. Like Jupiter has got all the planets going around, and Jupiter, along with all its, it's a satellites. Along with all its satellites, is going around the Sun. No? So his proposal was, Sun has got all the planets other than Earth, no? Going around nicely, and the entire system is going around Earth in an elliptic orbit. So, I mean, that's almost correct, in the sense of relativity wise, it is okay. As long as, see, you can say Earth is going around the Sun in an elliptic orbit, or reverse also is true. Sun is going around the Earth in elliptic orbit. You just see that. You see the observation, it will be correct. Except that there is a difference. Here, when the Earth goes around the Sun in the elliptic orbit, Mars or Venus is not going to tag along with Earth. No? So, whereas, if you assume that the Sun is going around the Earth, now along with Sun going around, he is carrying all the other planets also around. No? You see, that it should be the picture. No? That is a bit difficult to imagine, but that's what they thought was correct. So Tycho Brahe actually believed that geocentric only, because they had, like the earlier Greeks, they always had a problem of 1,000 miles per hour breeze on the surface of the Earth is not possible, so they didn't believe. In fact, that's got a scientific name also. One person studied that it actually happens, because we know it has to happen because Earth is spinning, once per day. So there is around approximately 1,000 miles per hour breeze, which is going from east to west, right? So obviously that is happening, and that is a Coriolis effect. A scientist, Coriolis, I think, did some research into those areas and produced a thesis for that. That is happening. That is different. But these people refuse to believe that. So. But he had good numbers for Mars positions over a long period of time, right? So, nearly 20 years. So what happens at that time is the question. We get two extremely important astronomers, physicists after this. After Tycho Brahe published the results of Mars observation, one is Kepler. I don't know, probably misspelled it. Should be a single P maybe, or double P. Kepler. Johannes Kepler is one master. Doesn't look correct. Let me write Tycho Brahe's name also. Kepler was a research scientist interested in astronomy. He came to this observatory where Tycho Brahe had done the observations for decades at a time, and he said he's very much interested. I want to look at those ledgers. Because he was junior, I didn't permit him to go through those numbers. Like I said, somebody had to make head or tail of. But then around 1600, I think, Tycho Brahe died. After his death, Johannes Kepler was senior in that organization, so he could get hold of all those registers and study the position of Mars in a much greater detail, and came up with Kepler's laws of planetary motion. Is that a single P or double P? People can decide. I'm unable to make up my mind. Because these laws are followed, he realized that the Mars position was calculated exactly, right? So obviously he said if it is be true for Mars, it should be true for Earth also, it should be true for Mercury also. So that's why he called it laws of planetary motion, Kepler's laws of planetary motion. There are three laws here, exactly like what we had for Newton's laws of motion. First law is the orbit is not circular but is elliptic orbit of planets. That is the first observation, first law of Kepler's law. The second is aerial velocity is constant. Let me just explain that. What is aerial velocity? If you take the sun or center of the sun, and I've got a planet here, take the center of the planet and connect the two with a line. And when the planet is going around the sun in an elliptic orbit, this line, if you treat that as a broom, is sweeping space. You can see sweeping space. So at given intervals of time, it sweeps an area in the space. That's the area swept per unit time. Every second is going to sweep that area. He said that area swept, regardless of, because of the elliptic orbit, sometimes it becomes closer to sun, sometimes it is farther away from sun, sometimes it is faster, sometimes it is slower, it might happen, but then this aerial speed remains the same. So the aerial velocity remains a constant, which really means when it is very close to the sun, it is going to sweep a much longer distance. For the same time, the same unit of time, when it is farther away, it travels smaller distance, but nearer, it travels longer distance, so that the area under the curve, area which is swept by that line remains constant. That is the second law. And the third law has got to do with the period of the revolution around the sun. How long does the planet take to go around sun once? What we call 1 year in the case of Earth, because we have kept that as a unit of time. Earth takes 1 year to go around, right? So he said the farther the planet, longer they are going to take. And in fact, that time period squared is proportional to r cubed. That means 3 times the third power of the distance. So as the distance increases, the time period also increases drastically. So that is the third law of Kepler's laws of planetary motion, which is all correct. And once these laws were in place, people could compute the positions of any of these planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune and Uranus and Neptune perfectly, almost perfect to the mile, so to speak. They could calculate because this is all correct, almost correct. So I think we should pay great respect to Johannes Kepler. We should have called him father of astronomy, but we don't call him. That is there, because around this time we got another gentleman who came around, who is in our local language, I might say, is the grandfather of all their brilliances. No, take the brilliance, each of them is brilliant in their own way, in their own field, in their own respect. But now we have one person who is, that means Brahe led to Kepler, right? Isaac Newton. He is known as the greatest physicist of all times. At the time of Newton, whatever subjects of mathematics were there, he was responsible for taking each of those fields forward by leaps and bounds. He is one of the most active persons. He has contributed in physics, in astronomy, mathematics, optics, sound. You talk of the subject, he has contributed massively. Plus, whatever contribution he has made, other people beyond him were able to develop into much larger areas of the respective fields, like physics or chemistry. I don't think he did, but mathematics, physics, astronomy, all these areas definitely are much better off today because of Newton. So Newton is one of the greatest persons of the time, and all he did was he took this Kepler's laws of motion, which are correctly, he's got three laws. He's not said why it should happen. He's only said how it should happen. How we can explain the positions of various planets. He has given equations for it. Equations are there. Those equations are correct. Now the question is, why should that happen? No? So that is what he was asking himself. The reason, like I wrote earlier, is Gurutvaakarshanam, but that was not known at that time. People didn't appreciate. Probably one or two astronomers were thinking of gravitational attraction, but they had not put it into proper words at that time. And Newton wanted to do that. For that, of course, first thing is he has to figure out. Newton had a couple of problems at this stage. Let me discuss that because that might give us some inspiration, some interest in the subject. I can tell you what Newton finally did as result number 1, result number 2 and result number 3. That's not a big deal. I don't want to do that. I would like to go ahead thinking in the way Newton was thinking to solve this issue or come to some conclusion on this issue. So we'll look at that. Okay. So now, first thing is, if you look at the Kepler's laws of motion, obviously we have no problem with that first law because that is elliptic orbit. Yes, elliptic orbit. Why elliptic orbit? That we'll see. That's a different issue. But at least we can decide on this elliptic orbit. Correct? Now we come to the second law. Second law, right, which says that aerial velocity is constant. Newton's first I have to explain that. First, you have to explain the aerial velocity, why it should be constant, right? So for that, let's just do a small analysis, geometry, so to speak, with astronomical distances. So we have the center of the sun. So I'll write sun as a small circle. It's huge actually, diameter wise. Then we draw a straight line and say that is the center of our planet. Correct? Now, if this planet were not going to go in the elliptic orbit, the question is, we are talking of aerial velocity. I want to know what is this aerial velocity. Supposing it is not going around the sun, where it would be going. It has got some speed, of course. Planet is traveling at some speed. So obviously it has got a tangential speed. So if it is not going around, it would have traveled straight up to one specific point. But instead of that, because of the elliptical orbit, it traveled to a different point. Correct? So let's just join these two. So without, supposing sun was not there, it would have swept the area of one triangle here. So I got two triangles, really speaking. So if you want to call the center of the sun as O, this planet is P, so I got a point Q and a point R. So I got a triangle OQP. area of the triangle is what it would have swept if it had gone straight up towards north. But instead of that, it went up. In addition, it went left also. Left is actually horizontally it has gone left to the point R. But if you consider this distance as a very small distance, make it very small, infinitesimal distance. What is infinitesimal? Is something like infinite. Infinite is indefinitely large. That means it is very large, indefinite. That largeness is not definite. You can keep increasing it as much as you want. Same thing exactly in the other direction. Infinitesimally is indefinitely small. You can take it as 1 foot. You can take it as 1 inch. You can take it as 1 micron or whatever distance you want. Whatever small distance that you want, you can visualize for that. When you do that small distance, this arc that you see here from P to R will actually become a straight line. Now it's a small straight line, and this horizontal RQ actually becomes parallel to that. So that means actually we can say, we can join this with a straight line. Now I got 2 triangles here. OQP is one triangle, which is what it would have swept if it was not under sun's influence. OPR would be actually is the area because it has been affected by sun. So what is it? How do you compare these 2 areas of 2 triangles? Both these triangles are the same base OP and they have the same height, so they have the same area. So aerial velocity must be constant. So that second law is simple. It's always constant, no problem. First law is there, second law also is there. In fact, whether it is elliptic orbit or not, whatever, it can be a parabolic or hyperbolic or any other circular, any path. When you have this, if you look at infinitesimal quantities, you will realize aerial velocity must be constant. If there is nothing from the sun, nothing from the sun. But now, indeed, there is something from the sun. So that is the third observation, is that there is something from the sun because of which this planet has travelled towards the sun some distance, correct? This is actually, I'll write it another way around. I'll write one more point here, I'll call it T. That means from P, it was supposed to go to Q. Instead of directly going to Q, it went to T and then went to R. So that means it has travelled towards sun some distance, correct? So there is and every time, every point on the ellipse, same thing is happening. So it is travelling towards the sun some distance, is also going in the tangential direction. Therefore, the tangential direction itself has become folded into the elliptical shape, right? So now, what is this? Why is it going towards sun? So there is an attractive force. So that is the force of gravitation. And he calculated, because the orbit is elliptic, you can calculate that gravitational force. And that, in some gravitational force, we say I've got a force. Remember, Newton's laws of motion is already there in Principia Mathematica. We got the object at rest, object with a force F is equal to ma is already available. So if there is a force which is being applied on this planet whose mass is m, acceleration will be a, right? So that means, regardless of this whatever mass which is there, there is a fixed acceleration towards sun, correct? There is an acceleration towards the sun, and that is a function of the mass of the sun. So that is the decision that he took and said there is a attractive force which is between any 2 objects. Let's call it a big object mass is uppercase M, small object mass, because this force reduces with the square of the distance. Distance is more, force will be less. Okay? And there is one constant here to adjust for initial values. So G m by r square. So this is the gravitational, Newton's law of gravitation. And Newton, I'll tell you where he took this equation. Okay. So this force, Newton thought if it is happening between Because the example he took was Sun and Mars, correct? So, if a Sun is attracting or exerting an acceleration on Mars, it should be doing the same thing on Earth also. It should be doing the same thing on Mercury also. So, it should be common. Obviously, what is the difference between that? After all, they are all planets. And same way, Earth itself must be exerting a similar attractive force on the Moon also. So, that means, why don't we generalize and say this is a universal law of gravitation, not just for Sun alone on planets. It's a universal law. Any two objects which have masses, you have g m1 m2 by r squared, is the gravitational force of attraction. Only thing is, unless this capital G value is so tiny or so small, that unless this mass m is massive, the effect is negligible. Even here, if I stand next to a mountain, definitely there is a gravitational attraction, but then that is negligible because the weight of the mountain is not enough to compensate for the smallness of G. Whereas the mass of the Sun, capital M, solar mass is massive. That is very massive. And obviously that's why you have appreciable force being applied on each one of the planets. They are forced to go around in elliptic orbit. So he presented this Newton's universal law of gravitation. And one of the things which Newton has made comment on his own, which inspired him, I don't know whether to develop this equation for some other purpose, but inspiration. He got an inspiration because of decimal fractions of Indian arithmetic that he saw in one of those Latin books of Khwarizmi or somebody else. I don't know. So he was basically, he got inspired by those decimal fractions. What is a decimal fraction? I got a decimal number, right? You can write any decimal number, 1.234, whatever. Now, I don't like this dot. No, I want to remove it from there. So just multiply and divide by, in this case, 1000. So 1.234 is same as 1234 divided by 1000. We can cancel some common factors here. Not necessary also. So you get what is known as a decimal fraction of integers, two integers, and we got a decimal fraction. And there is some work people have done. There is one person, one Muslim gentleman by the name Al-Kashi. He was excited about these decimal fractions. He wrote an entire treatise on decimal fractions, how they behave, how to add, subtract, multiply, divide, and what are their properties. A number of actions on that. And that, of course, he wrote in Arabic, and that got translated to Latin, which I suppose Newton read that and got inspired. So, where the inspiration comes, I think, is not important. How it comes is not important. The fact remains that inspiration should come. So that's the main deal here. That is one aspect of this whole business. So people thought this is the end of astronomy. Subject is over now. Everything is finished. Right? Is attraction is there. So, obviously, there is one question has not been answered after all this. Right? Why is it there? Now, suddenly, Sun decides to attract Earth, which is 200 million kilometers away. See, the distance between Sun and the Moon is 200 million kilometers. Unimaginable distances, those astronomical distances. And is able to exert that kind of pull on such a massive object like Earth, to force it, like literally holding the Earth with a rope and then pulling the rope. So, how is that? Why is Sun doing it? I mean, why is he doing it? Or is he doing it? Any other explanation? No, obviously, is required. So it's not the end of the world for astronomy. Something else needs to be done. But then, like earlier, we had to wait for 200 years for the next development, another 300 years for Al-Kashi to come, another 100 years for Newton to look at it, another. Obviously, we had to wait for another 270 60, 70 years for the coming of another person. I won't just call him brilliant. Yeah, see, calling him brilliant is an understatement because all of these are brilliant people, right? So, and you call this person also brilliant is insult to that person. No, who is that person? Albert Einstein. Date is 1905. So 1905, he came up with the theory of relativity. Which completely explains why sun is attracting Earth or whatever. Sun is actually not attracting. Space itself is twisted. Because of the mass of the sun, space itself is twisted and Earth thinks it is actually downhill there. No? So it looks like downhill. You can't make out from here because this twisted space of 3 dimension twisted in the 4th dimension. So 3-dimensional people like us cannot feel it. We don't understand how it is downhill but in the same space. No? So that's what it is. So that's what he explained. You would think that is the end of the world, but it may or may not be. Again, see that scientific research keeps going on and on and on, and people discover new things. Now, coming back to Newton's other problem, like I said, he had to calculate these movements of the planets in some kind of infinitesimal calculations, right? Now, such methods were not available in algebra, not available in geometry. So far, it's not there. He said, boss, what do I do now? I need to compute this small number multiplied by another small number divided by small number, take square root. There is no standard method. It's not available in mathematics. So, even though he was not a mathematician, he said, all right, I will design a new branch of mathematics and call it calculus. Actually, I think he didn't call it calculus. It's infinitesimal computations, infinitesimal calculus or whatever name that he gave. So he gave that calculus. So he had to invent calculus to help him calculate these astronomy figures. No? So for that, that is another end result of Newton's work. So he contributed that massively to mathematics also, even though he was actually not a mathematician in the true sense of the word. He was a physicist actually and an astronomer. So he gave that calculus to us. Around the same time, another gentleman called Leibniz also invented calculus. So we give a joint credit. No? So we write that as a Newton dash. You can call it Newtonian calculus or you can call it Newton-Leibniz calculus. Gottfried Leibniz. So Newton-Leibniz calculus is what we call, because almost around the same time they invented calculus. How Leibniz invented calculus, Newton at least had a need for it, for doing this infinitesimal calculations. Leibniz didn't have any need at that time. He was not even a mathematician, he was a philosopher actually. But why he did that, I'll explain to you at some other time. That is a different issue. But now you can think of Newton, Leibniz as fathers of calculus. I think that's a good decision to come to. Now, once he invented this infinitesimal calculus, remember his only business was to get his end result of universal law of gravitation. So he would skip steps, or he would go ahead and work instinctively and so on. So it would not be a very rigorous mathematics that he did. So we need people beyond that point to come around and give rigorous explanations for all that. We need a proper development of calculus as a subject. We need that definitely. And there we have people like Brooke, Taylor, Roll, Madhava, all these people helped in improving. I mean, Madhava actually earlier than Newton, but anyway, all these people helped calculus become the subject that it is today, right? Now, I would like to stop there. I can talk about some of these people, doesn't matter. You can always read that on your own. Remember, all this information, I didn't simply pull it out of thin air. I educated myself, did research and found out most of this information. And I would have made a mistake also there, definitely, because presenting so much of detailed information, somebody is definitely likely to make a mistake. Plus, if you want more details about a specific person or life history or some other aspects of that particular field area, I suggest you look at it in the internet. And one of the very reliable sites for that is Wiki. Look at those topics in Wiki. Wiki, I found there is only one problem with this Wiki, is that it is a hypertext markup language. No? So, that means when you open a topic, you may get a document of some 4 pages, but then there are so many hundreds of words there in the document. When you click those words, it opens up another document which might have another 1,000 words of colored words, which can open other documents and so on. So it is a whole series of nested documents. So you have to be very careful when you read these documents. But definitely you can go ahead and read that literature anytime you want. And the only purpose of my presenting this much information to you is, like I said earlier, is to have some sort of, I don't know, I won't call it inspiration, at least a bit more interest in mathematics. If you can generate, in some of you at least, I believe I would have served the purpose of doing this in the first place. No, I'm trying to do this only for that purpose, that generally people should not find mathematics as a difficult subject. Whether you want to do mathematics, whether you want to do research in mathematics, or you only use mathematics as part of your other subjects, that is immaterial, that is different. Or don't want to use mathematics, doesn't matter what you want to do with it. But then I don't want you to say mathematics is difficult. It is not. It is one of the most logical subjects that I can think of. Every step, like I said, most of the steps that Newton used in deriving his Newton's law of gravitation, people have picked holes in those proofs and say, you can't write simply like, you can't simply assume something which is not true. So it's got to be proved in a rigorous fashion. So people have spent lifetime on those aspects of mathematics, and one of the reasons why it has grown so big also, right? So, but now you see the interconnection between why it was astronomy and astrology first, along with arithmetic. Then we added geometry there because we wanted to do measurement on Earth to help us do measurement in space. Earth also it is required, measurement in geometry is required. Then we had this decimal system, which is the 10 base. Now it is universally used of Hindu Arabic numerals, and that is one of the best number systems ever designed by human beings. It's done a fantastic work towards that. Then we had people like Khwarizmi designing or telling us how to write algorithms. So algebra came into being. We got something called algebra, and algebra exploded on its own as theory of equations. We'll see some of those aspects at a later stage. Then trigonometry as a separate subject, a study of triangles with these trigonometric functions. Now, it's not just study of triangles. Geometry itself has got a lot of study of triangles. Here we are talking of trigonometry in terms of study of trigonometric functions. We have the sine and cosine, then tan and secant and cosecant and all those functions and their properties. Now, that itself became a separate subject of mathematics. But their origins is here in that Ardha Jya. Now, that is where sine took its birth. Kotijya, the sine and cos took their birth there. So, you see why it came into being, because of the same circumnavigation or parikramana, when circles and movement along the circular path, what happens to the horizontal and vertical distances. So that is the basic reason why we got trigonometry as part of the geometry, correct? Then Newton came around and gave us calculus because he thought it was required to do planetary movement computations. So we have the calculus also. And once you have calculus, it's always good to see if, can we use it for something else, so obviously, so we would like to use it wherever we want. In fact, I'll give you a couple of very simple examples of using the calculus, like finding the volume of a sphere, or volume of a cube, or volume of a cone, and so on. You can do that in just 2 minutes, what people, what Greek mathematicians like Euclid or Aristotle or Pythagoras himself, tell him how to find volume of a cone, for example. He will do that. He will definitely give us the answer, but then he would make a lot of construction and build some hexagons around underneath that, octagons above that, and then say, I will take the thickness, make it reduce and less, and something he will do saying this is less than that, but greater than this, but less than something else and greater than something else, and so on. And finally, after 2 days, he'll come and tell you, sir, I know the volume of cone is 1/3 pi r squared h, 1/3 pi r squared h. Volume of a cube is 4/3 pi r cubed, right? So, but with the calculus, you and me, ordinary mortals, we are not such brilliants. We can do that in 5 minutes. In 2 lines, we got volume of cone or volume of a sphere. So, calculus, that infinitesimal calculus, makes life so simple for calculations. So it has become, I think they don't call it calculus anymore. It is part of our algebra. It is part of our mathematics. So I'm saying, don't get suddenly say, we got calculus so difficult. So don't have to think like that. You have to see that just another side branch, which came because of a necessity, but then people found other uses for it. And that's how you have to look at those different branches of mathematics. And everything is methodical. Let me assure you, like I showed you a simple example of Kepler's second law of motion, which can be very easily explained by a simple thing like area of a triangle. So it's a very simple thing to explain. So everything is logical. There's no question on that. And we need to look at that. What I suggest is that we can start with, in the next session, we can start with some simple geometry. So that is basically Euclid's elements. I'd like to start with that, and we'll discuss at least a few fundamental theorems and see what are the proofs and why people find geometry difficult. I think that's the first question that I would like to take up, and see how we can simplify that understanding. And same thing we do for algebra and for calculus and trigonometry, I suppose. So we'll do that.